Look at functional groups, the groups that make our organic molecules useful. So let's just go through a little bit systematically and identify the different sorts of groups that we can have. And in a couple of chapters' time, we're going to be looking at techniques which recognise different bond types together in a molecule. So it's useful just to identify those now. So if you've got just a C and a H and single bonds, CH3 on the end of a molecule is called a methyl group. CH2 in the middle of the molecule is called methylene group. And of course we've just got carbon-hydrogen bonds in those. Alkenes, alkynes, alkanes have got single, double, triple bonds. They're the bond types present. Haloalkanes, halogens, group 17. We mean carbons with a chlorine attached, a bromine attached, an iodine attached, or even a fluorine attached, or if you really want, an astatine attached. Anything in group 17 is a halogen and it forms a haloalkane. Bond type's pretty obvious. Now in year 11 we looked at alcohols, and we recall there are primary, secondary and tertiary alcohols. So first of all, the primary alcohol, the hydroxyl group is on the end of the chain. Secondary alcohol, the hydroxyl group is in the middle of the chain. A tertiary alcohol, the hydroxyl group is in the middle of the chain on a branched carbon. So a primary alcohol, the carbon that the hydroxyl group's attached to has 2 hydrogens. Secondary alcohol, the carbon has got 1 hydrogen. Tertiary alcohol, the carbon has got no hydrogens. Bond types in an alcohol, in that functional group, are going to be carbon-oxygen and oxygen-hydrogen. Carboxylic acids. Remember the carbon double bond oxygen and an OH group on the same carbon. And 3 different bond types. So 3 bonds are all present in a carboxylic acid. Esters, on the other hand, will often have a same molecular formula as a carboxylic acid, and that's of course what we get when we react an acid with an alcohol. And they've only got they don't have the OH bond. It's a fairly important fact that we'll see later on. So it's carbon, single bond oxygen, so we've got an oxygen in the chain between 2 carbons, and one of those carbons has got a carbon double bond oxygen. So that little bit of polarity, of course, is what gives biodiesel its distinct properties. Amines, it's a nitrogen attached to a carbon with one or more, with usually numbers of hydrogens attached, not always. Aldehydes and ketones. Not sure whether you did these in year 11. They're where you've got a carbon double bond oxygen as your functional group. If that carbon double bond oxygen is on the end of the molecule, it is an aldehyde. If it's in the middle of the molecule, it is a ketone. That's the only bond type, distinct bond type present. Ethers, where you have a single bond between 2 carbons, and neither of the carbons has got the double bond oxygen like an ester, so it's between 2 hydrocarbon bits. It is an ether, less polar than an ester. General formula ROR prime. That's using R just to stand for any length of alkyl side chain. Amide, what you get when you react to carboxylic acid with an amine. That's the peptide group in biology. It's an important one for us in this course too. So it's got 2 bits to it. You've got the carbon joined to the nitrogen in the chain. The carbon's got a double bond oxygen, the nitrogen's got a hydrogen. So both, that's a very important unit. Of course, that enables hydrogen bonding. You've got a hydrogen attached to a nitrogen, means there's hydrogen bonding, which is, of course, is crucial in proteins. Okay, chloroalkanes. That's one class of haloalkanes in which the halogen is a chlorine. They're the most common haloalkanes. So one or more hydrogens replaced by a carbon, you can have chloromethane, you can have trichloromethane, or you can have various isomers, so 2-chloropropane. Useful as intermediates in turning alkanes into something a little bit more useful. Chlorohydrocarbons, chlorofluorocarbons, halocarbons of course have been found to destroy the ozone layer, so they're being less and less used in organic chemistry these days. So just name and write semi-structural formulas for these. If you could, submit your answers on Google Classroom. And like I say, you can have a whole range of different haloalkanes and similar naming conventions. So fluoroethane and 1,2-dibromopropane. Okay, alcohols, much more interesting, much more useful. Naming, if it's a suffix, if it's the primary functional group, it'll name the molecule an ol. If there's something else which takes priority in the naming, it's called hydroxy something. The name of the functional group is a hydroxyl group. The name of the class of compounds is an alcohol. So if you're asked to name the functional group, remember it's hydroxyl. So here we've got a series of primary alcohols. We've got methanol, we've got ethanol, and we've got, what's that? Ethylbutanol, 2-ethylbutan-1-ol. Remember primary, secondary, tertiary alcohols, whether the carbon bonded to the hydrogen, to the hydroxyl is bonded to 1, 2 or 3 carbons. Only primary alcohols can react to form carboxylic acid, so that's a synthesis that we'll be looking at in the next chapter. We want to make carboxylic acids from alcohols. Well, since the carboxyl group has to be on the end of the chain, then if we're going to react an alcohol, it has to be an alcohol with the hydroxyl group on the end of the chain. So this hydroxyl group it's a primary alcohol, and naming it, of course, we're going to number the carbons from this end, so it'll be 3-methyl-butan-1-ol, amyl alcohol. This is a secondary alcohol because the carbon is attached to 2 other carbons, xan-3-ol, and here we've got a tertiary alcohol. Carbon is bonded to 3 other carbons, and it's methylpropan-2-ol, commonly called tert-butanol. A lot of these fairly common organic molecules have got names which are used more commonly than their formal IUPAC names. You get to recognise some of them after a while. Amyl, of course. The hydroxyl group, of course, can undergo hydrogen bonding, and that gives alcohols their distinctive properties. Gives them a higher boiling point and increases their water soluble. Now when you're drawing alcohols, draw the OH group out. If you're asked to draw a full structural formula, draw all bonds, it's really easy just to forget that little bond, just write OH on the end and it'll lose you a mark. Carboxylic acids, COOHs, the name of the functional group is a carboxyl group, and it always takes priority. If there's a carboxyl group in a molecule, it's always, the name of that molecule is always going to end oic acid. So have a look back at that Lipitor molecule that I started off with. That is named, that's an oic acid, heptanoic acid, I think. Now, there's no primary, secondary or tertiary with carboxylic acids because the carboxyl group has to be on the end carbon because it takes up 3 bonds. So it's just the number of carbons, methanoic, ethanoic, butanoic. Short chain carboxylic acids, ethanoic acid, acetic acid, are completely water soluble. Vinegar, of course, being what that is. But with carboxylic acids, we get a lot of long chain carboxylic acids, 10 carbons or more. Now, they're called fatty acids because they're carboxylic acids you can get out of fats, and they have very low solubility because you've got a very long hydrocarbon chain. The hydrophobic nature of the hydrocarbon chain completely overshadows the hydrogen bonding with the carboxyl group. Amines, functional group named amino, and as a suffix it is named as amine. Now, amines, there are a whole lot of ways you can name them that are commonly used. We, of course, teach the IUPAC method that BK are after, so try and ignore the other names that you come across for these molecules. So, 1 carbon with an amino group, methanamine. 3 carbons, amino group attached to carbon number 2, 2-propanamine. And here we've got 2 functional groups. So the carboxyl group takes precedence. So it's 2 carbons makes it ethanoic acid. We've got an amino group attached to carbon number 1. Well, it has to be on carbon number 1. So we've got amino ethanoic acid. And the biologists amongst you hopefully will recognise that as glycine, the simplest amino acid. Polar, therefore hydrogen bonding, and acid and amino groups actually form ions when they're dissolved in water, biologically in particular, so you get ionic attractions forming in that case. Amino acids with an amino group and a carboxyl group are obviously the building blocks of proteins that we'll look more at later in the course. The base, just as carboxyl groups can act as acids, the amino groups act as bases. So it's that lone pair on the nitrogen accepts a proton to form that. And alkanamines is the basis of the naming, as we saw. Now, primary amine. Primary amines, the nitrogen is bonded to 1 carbon and 2 hydrogens. Each one of those is a primary amine. Secondary amine and tertiary amines, the nitrogen is bonded to 2 or 3 carbons. So a secondary amine, the nitrogen is bonded to 2 carbons. Tertiary amine, the nitrogen is bonded to 3 carbons. Still got its lone pair in each case, so still can act as a base. Amides, where we've got the carbonyl group beside an amino group, the carbonyl group coming from a carboxylic acid, and that's the peptide group in biochemistry. Note that when the carboxyl group loses hydroxyl, loses its OH when it's reacting. It's just a C double bond O left behind. We call it a carbonyl group. So it's a carbonyl attached to an amine. Primary amides, one carbon attached to the nitrogen. Secondary amides, two carbons attached to the nitrogen. And you can probably guess what a tertiary amide would be. Secondary amides, of course, are interesting to us in biochemistry. Aldehydes and ketones. Now, you need to be familiar with these. You don't need to know too much about their properties or their naming, but you have to be able to recognise what it is, that it's an aldehyde or a ketone. And that's based on the location of the carbonyl, the C double bond O, in the molecule. Aldehydes have got a carbonyl group on the end of the molecule, so two carbons, that is going to be called ethanol, the naming convention. One carbon has to be on the end of the molecule, of course. Methanol. Now these are much more commonly known as acetaldehyde and formaldehyde. Ketones, the carbonyl group is in the middle of the molecule, so we would call this propanone. If we're outside of the chemistry classroom, it's called acetone. Nail polish remover and a common organic solvent. Okay, have a go at these questions, submit your answers, and you will get the solutions. Let's start with that one. Naming with multiple functional groups. So basically, when you get a combination of functional groups, one of them goes at the end, that's the major functional groups, goes as a suffix, and all the other ones go as prefixes out the front of the molecule. And this is the table that gives you the order of precedence. You need to have a basic idea of this order. Carboxyl groups are number one. If it is a carboxylic acid, it is going to be called, the name of that molecule is going to end oic acid, never as a prefix. If it's an ester, likewise, it's always going to be an O8 molecule. Alcohols, if they're the major functional group, it will be an ol. If it's prefix, i.e. if there's one of those two present, it will be hydroxy something or other. Amines and aminos and amines. Aminos if it's at the front, amine if it's at the back of the name. Enes and ines sort of slip in there after the number of carbons and before the suffix. Halos and alkyls, i.e. group 17 atoms and hydrocarbony side chains, have to go as prefixes, and they are actually equal in precedence. So it's whichever one of them is closest to the end ends up is numbered from. Number the chain from the end closest to the highest group. Like I say, they're equal, so it's whichever one of them is closest. Okay, so name these. So how many carbons have we got? 6. Let's look at our functional groups. What have we got? We've got a chloro, we've got an amino, and we've got a hydroxyl. Which one of those takes precedence? Which one of those is closest to the top of that table? Hydroxyl. This is an ol. This is hexanol, hexan 1-ol. We'll number the carbons from that end. And then the other groups will be named in alphabetical order at the start. So 4 amino, 5 chloro, hexan 1-ol. Here, major functional group, Well, there is no major functional group. They're actually equal in precedence. So it is just hexane. Nothing on the end, it's just hexane. Number from the end closest to either one of them. In this case, it's going to be closest to the methyl, so it's going to be from this end. And put them in alphabetical order. So what have we got? We've got 3-fluoro, 2-methyl hexane. Okay, have a go at naming these and submit your answers, and then we'll move on. Okay, isomers and functional groups. Basically follow the rules as we did for alkenes. So start off with a paired alkane, draw all the isomers of that many carbons, and then work out all the different places you can put that functional group. Of course, carboxyl groups have to go on the end. So have a go at drawing the isomers of those two. So remember, how many isomers have you got for butane? 4 carbons in a row. You've got 2 of them. You've got N-butane and you've got methylpropane. So for question 1, where are all the different places you can put an OH group on N-butane? Where are all the different places you can put the OH group on methylpropane? And then the same with carboxyl groups for question number 2. And there'll be a few less for that one, of course. Finally, a little add-on to the topic in which we learn a technique. If you're given the molecular formula, it's useful to know how many double bonds are in the molecule. And a little technique that we apply is called the degree of unsaturation. So this one's got a double bond, so it's got a degree of unsaturation of 1. This one's got a double bond and a ring. Both of those contribute to the degree of unsaturation. This has a degree of unsaturation of 2. Just a ring, degree of unsaturation of 1. This one's got, what's this one got? It's got a ring, and it's got 1, 2, 3 double bonds. That gives us a degree of unsaturation of 4. Now, sort of looks a little bit clunky when you first look at the method, but it rapidly becomes very easy to use. Now, so we go through the rules this way. We take the molecular formula and reduce it to a hydrocarbon. So any oxygens, we just forget about them. Any halogens, well, we just pretend they're hydrogens. So that's pretty automatic because all a fluorine does is it replaces a hydrogen, so it pretty much acts as a hydrogen anyway. And then nitrogens, they're the tricky one. You leave it off and you subtract 1 hydrogen. So just delete it and minus 1H. Now that gives you the formula of a hydrocarbon. You then compare it to the alkane with that many carbons. Then there'll be a difference in the number of hydrogens usually. Every 2 hydrogens less is 1 degree of unsaturation, usually 1 double bond. So it becomes easy when you actually see it done. So acetone, reduced to a hydrocarbon, it's got an oxygen there, we'll just leave that out. So C3H6. Compare it to the alkane with 3 carbons. Well, that's propane, C3H8. 2 hydrogens less is a degree of unsaturation of 1. Every 2 hydrogens less is a degree of unsaturation of 1. Now you can do that with a little formula if you want, but just look at the hydrogens. Every 2 hydrogens is a degree of unsaturation of 1. That means that's got 1 double bond, or could conceivably have a ring. It'd be a fairly reactive little number if it did. Now this one, reduced to a hydrocarbon. Well, first of all, we just forget about the oxygens and we remove the nitrogen and subtract 1 from the number of hydrogens. So C4H6. Now, 4 carbons. How many hydrogens does a 4-carbon alkane have? Does butane have? Well, 10 of course. And this one's 4 hydrogens less, so that's a degree of unsaturation of 2. Every 2 hydrogens equals a degree of unsaturation of 1. So 2 double bonds, probably, perhaps a ring there somewhere, or maybe even just a triple bond. Triple bonds count as degrees of unsaturation of 2. Now this one, reduce that to a hydrocarbon. Well, halos, chloros, fluoros, bromos, iodos, all just pretend they're hydrogen. So that becomes C4H10. What's the alkane with 4 carbons? C4H10. So no difference, no hydrogens less. That means a degree of unsaturation of 0. It is a fully saturated molecule. No double bonds, no rings. Have a go at the question, and that's the end of